So, in today's lecture, we will cover nonlinear optics in a nutshell for the fourth session. And while we key in on the same reference textbooks, and we have the book by Robert Boyd, with which we should pay specific attention to for this section of the course. We also thank Professor Trebino for his very pertinent inputs and materials. Now, in this lecture, we will recap a bit of what we did in the previous week, mainly regarding the physical origin of refractive index and absorbance. We can say the real and imaginary parts of the refractive index and the physics that underlies its origin and so on. And in today's lecture, we will dive into optical nonlinearity and explore various aspects of it. Okay, so why are we here? Because of our agenda with optical light pulses, especially of the kind that we are seeing here, which we now know a whole lot about. In terms of nonlinear optics, specifically, we want to understand the physical origin behind refractive index, the real and the imaginary part, in terms of the current formalism of both linear and nonlinear optics, and then motivate ourselves to understand the origins of optical nonlinearity and low order harmonic processes, especially second and third harmonic generation, because attosecond pulses are high harmonic generation. So, when an atom encounters light, typically this picture is good. The incoming radiation essentially leads to dipolar oscillation of electrons. If we excite the electrons successfully, part of the beam is absorbed and the remaining part is simply refracted, or it's phase modified. The phase of the beam is modified in the process owing to the atomic response. Atomic response also leads to the absorption spectra, which are characteristics of atoms, molecules, or condensed phase matter. Now, we looked at what light does to matter and how we can model this. In this case, essentially we pick up on a model where the electron cloud is bound to a point like nucleus, and the driving light field essentially acts on this electron cloud owing to the Lorentz force. So, this is we can call this the Lorentz oscillator model, but essentially it is a forced damped harmonic oscillator. So, all the terms in this equation are linear. This equation has a solution in terms of the driving field to be where the displacement of the center of charge of the electron cloud x e of t is written in terms of the electron's charge by mass, and the resonant frequency of the driver, of the driven system, not the driver. Omega naught is the eigenfrequency of the atomic oscillator of interest here. It is one of the eigenfrequencies. This will hold for all of them. Then omega is the driver's frequency, the frequency at which the light wave oscillates. Gamma is the damping constant, and the rest is regarding the wave that is oscillating or leading to the electronic oscillations. And so, basically the amplitude of the electric field and the electron cloud oscillate on similar time scales, and we saw that if the driver is having a frequency much less than the resonant frequency of the atomic dipole, then the vibration is a pi or 180 degrees out of phase. And in the other case where omega of the light field is much greater than the eigenfrequency of the electron cloud nucleus electron cloud system, then the oscillation of the electron cloud is in phase. When these two are about equal, we hit a resonance and the electron cloud vibrates minus pi over 2 out of phase with respect to the light wave. These are the hallmarks of the atomic response of matter to light. So, this is what light does to matter. It makes matter undergo dipolar oscillations. Basically, that is the take home message. Now, we looked at the complex response of the atomic displacement x e of t. We can write this down in terms of a real part and an imaginary part. The real part, which in terms of the variable delta, which is the detuning of the applied electromagnetic frequency with respect to that of the native resonant frequency of the atomic oscillator delta. So, this is the real part is an odd function in delta, whereas the imaginary part is an even function in delta. So, the imaginary component is the is basically the absorption resonance that we can measure in spectroscopy, whereas the S shaped or Z shaped response is the real part of what will become later on the refractive index that we perceive. So, what does atom do back to light? That is the question. So, we deduced atomic response based on this classical Lorentz oscillator model, which is a forced damped driven harmonic oscillator where light is the driver. But then this also this is a classical model, but it is very analogous to an accurate quantum mechanical picture in the semi classical approach, that is the approach where we treat the light wave to be classical, but matter to have all the possible quantumness that we want. But then how does matter or atom give back to light? So, we looked at that. So, the total field is incident plus emitted field. We wrote down Maxwell's equations for a medium, okay, and then we got introduced to polarization, that is the dipole moment per unit volume. It is a field capital P, the superscript here L denotes the fact that we are assuming linear response. If we do, then the polarization field inside matter is linearly proportional to the applied electric field. This linear proportionality can still imply anisotropy, so that chi is not necessarily just a scalar, and chi can essentially become a second rank tensor chi ij. But then if I want to compute or model the complete response of this medium within a perturbative picture, then essentially the full expansion of the polarization vector or its components written as Pi is the first order term, if you wish, that is chi 1, which is the linear response. We have the second order term, that is the quadratic and the cubic response. All terms after the first are nonlinear response. We are not going to talk about this as yet. We will soon be talking about chi 2, chi 3 and others, but the point to note is that chi ij is a tensor of the second rank and E is the applied field. For a non-magnetic medium, M, the magnetization vector, is 0. Furthermore, if we neglect or ignore scenarios which contain free charges or free currents, which is what a lot of dielectric media especially for nonlinear optics would amount to, then the 4 equations of Maxwell will turn into div E is 0, div B is 0 and so on. We then understood that the induced polarization in the medium will lead to a source term leading to an inhomogeneous equation, wave equation for the propagating wave. This acts as a source term, but what is the source for the emitted radiation? That source is essentially the oscillating electron cloud. Okay. So, P is the polarization vector as a function of time. For every point in the medium of interest we compute this. Xc of t is the displacement of the electron cloud with respect to its new positively charged center that it is bound to. E is the electron and n is the electron number density in this medium, all of which can be computed even from quantum mechanical models and pictures, right. So, we essentially then wrote the polarization vector in terms of Xc of t and introduced the susceptibility chi over here. So, that P is epsilon naught chi E, and then substituted for P in terms of chi E, and in doing so we derived or arrived at the inhomogeneous wave equation. It is inhomogeneous because earlier the wave equation in this 1D case had d2E by dz2 minus 1 over c square d2E by dt2 is equal to 0. This was the homogeneous equation we had earlier. The right hand side was 0. Now, we have a term containing chi and the second derivative of E with respect to time. So, it is inhomogeneous. Nonetheless, we can now simplify this further and turn this into an equation which is not necessarily having the form of an inhomogeneous equation, it is the 0, it has a 0 on the right hand side, but then we have included here the term containing chi, and we have 1 plus chi appearing here in the numerator. As a consequence, this is now the equation for a wave propagating in this medium, which is non-magnetic and has no free charges or currents, with a velocity which is c naught divided by the square root of 1 plus chi. Okay. So, we saw this, and we defined also going alongside alpha, which is equal to k naught, that is 2 pi by lambda 0, lambda is in the wave, lambda 0 is in the wavelength of this wave as it would have been in vacuum, multiplied by the imaginary part of chi, whereas n, the refractive index, is 1 plus a half the real part of chi. We have here expanded 1 plus the square root of the real part of chi to be taking only the leading term in the Taylor expansion. If we do that, then we essentially have the electromagnetic propagating wave after having at a length z of the medium through which it is propagated to be E naught, the initial amplitude, multiplied by an exponential amplitude modification, that is e to the minus half alpha z, alpha being k naught imaginary part of chi, multiplied by exponent of I k naught n times z minus omega t. It is not n here, it is 1 plus half a chi, because we set n to be that. We call this 1 plus half the real part of chi, or the square root of 1 plus the real part of chi to be n. So, n now is the occupying the position in this equation of the real part of the refractive index, and therefore, 1 plus half the real part of chi is the refractive index, which we have been seeking so far, and so on. And in the medium, we essentially have the amplitude to be diminished by exponent of minus half alpha z, and similarly so. And we had as a consequence the notion of a complex valued refractive index, where the real part is the conventional refractive index, which is responsible for refraction and phase modification of a beam, whereas the imaginary part, which is alpha, okay, is related to kappa, the complex or the imaginary part of the refractive index and its absorption. Okay. So, this now works because the transmitted field in the medium is described by both alpha and n. We can further simplify this and write things down. Now, this is where we sort of begin some new stuff in this lecture. What we ought to now understand is, we have given ourselves the opportunity to understand the origin of refractive index from a very fundamental perspective. What do we mean by fundamental here? We mean exactly the following, that is, we are able to now across the what looks like almost the entire electromagnetic spectrum, or a sufficiently broad region of interest, mark various omega naughts which can occur for the same medium in different spectral ranges, all the way going from infrared to visible to ultraviolet to X-ray. Okay. So, omega naught 1, omega naught 2, omega naught 3 are 3 typical resonant frequencies, but note that they are in the infrared, visible, ultraviolet patch and near the X-ray respectively. Okay. So, all these correspond to 3 different resonances. They are all apart by a factor of 1000 in terms of the order of magnitude of the frequency of the electromagnetic radiation or photon energy. Okay. So, now what we can easily see now is that there are regions where the refractive index grows with frequency, n as a function of omega, okay. We have a region where dn by d omega is greater than 0. So, the region where this is taking place in the electromagnetic spectrum is said to be normally dispersive, or a region of normal dispersion. Normal as in regular, usual, the expected behavior of dispersion with frequency, alright. And where dn by d omega is negative, again because there is significant change of refractive index with frequency, there is dispersion, but since this is not normal, instead of calling it abnormal, we call it anomalous. Okay, so the regions of anomalous dispersion are shaded here in gray. We know that there is utility for this in technology, for example. So, if a pulse propagates in a medium with normal dispersion, it acquires a positive chirp. If one wants to compensate for it, one should ideally find another medium for the which has anomalous dispersion over the same range as the spectral content of the pulse. That will start compensating for the positive or even higher order linear positive or higher order even higher order positive chirp that the medium may have added as a baggage to our pulse, okay, as an overhead, it can undo that. So, light wave entering a medium, this is a great picture to have in our minds in terms of how the wave behaves in a medium. So, in air or vacuum, okay, let us say in this region, the pulse propagates unhindered and sort of nicely here. It is propagating from left to right, everything is in order, the wave is oscillating as it should. The propagation vector points to the right in this 1D model, the increasing horizontal direction of the z coordinate, and we can describe this very nicely by E0. E of zt is E naught at the value z is equal to 0, okay, and this remains constant, and simply we simply have harmonic oscillations, right. The wave is just a set of harmonic oscillations as we envision it to be. Then at some point this enters the medium of interest, okay, it enters the medium of interest, and inside this medium two things take place particularly. Even if the medium is say homogeneous and isotropic, apart from in this case even being having only a significant linear response, we ignore other responses in the medium. Then what happens? Then if the medium has no significant absorption, the wave amplitude would not have diminished, but if the medium has a substantial absorption coefficient, so that there is a depth of absorption, okay, there is significant absorbance of the beam, then we can define that length L or a depth L over which the intensity falls by a factor E being the exponential factor, right, it is 2.7 something. So, the 1 over E point in terms of the propagating wave, after propagating which the intensity is diminished by a factor of E, is called the absorption depth. And since we had for the intensity I is equal to I naught exponent of minus alpha L, for electric fields it was minus a half alpha L, right. So, therefore, this length, let us call this L 1 over E. So, the length L 1 over E would be 1 over alpha, we can call this the absorption depth. Across media we would be able to compare the absorption depth for that matter. It is just introducing another terminology, and the refractive index n plays a role, and the propagation vector inside the medium gets modified by this factor n. This is a good picture to have. k gets modified, so also this impacts the phase. Okay, immediately we can see that it impacts the phase. Okay, so absorption coefficient, therefore, since we have deduced this from a first principles perspective where the electric field amplitude E of z was obtained from first principles to be proportional to exponent of minus alpha z by 2 or minus a half alpha z, then the irradiance is just a square of this, right, is the square of the electric field amplitude, in fact the absolute value square. As a consequence, right, we can deduce just by converting from field to intensity this very important relation where I of z is equal to I0, the input intensity, times exponent of minus alpha z, and this is the famous if you wish Beer-Lambert law. Okay, we call it a law, but it is a Beer-Lambert equation or relation. We have just, it just popped out spontaneously as a consequence of our rigorous analysis. Now, we can further go down, drill down a bit deeper and ask where does alpha come from? Okay, alpha, but we know this already, alpha is the imaginary part of the atomic dipole moment, related to the atomic dipole moment or the displacement of the atomic dipole, right. As a consequence, we can associate alpha with the notion of cross section. Alpha, the absorbance, we can say is n, the number of relevant dipoles per unit volume, multiplied by sigma, the absorption cross section. Okay. So, or we can say the absorption cross section, sigma is absorbance alpha is the absorbance alpha, sorry, sigma is the absorbance alpha divided by n, the number of dipoles per unit volume. So, what is n then? What could be the interpretation of alpha? Not, I mean, what is sigma then? Sigma is the new thing that we have introduced, absorption cross section. So, what is this quantity? So, let us see what units it has. Okay. Alpha has units or dimensions. Alpha has dimensions of 1 over length, okay, because exponent of minus alpha L, times n has dimensions of 1 over L cube. So, this 1 over n has dimensions of L cube. So, this is L square, or sigma, the cross section, has dimensions of area. Okay. So, essentially what we are saying is that an atomic target, okay, on which the wave is incident, is acting essentially like an absorber. Okay, it is like a hand that captures a unit of electromagnetic radiation. You can say, you can even go down to the extent of, go into the extent of saying it captures a photon, it absorbs it, okay, presenting an effective area which is equal to the value of sigma. So, sigma, say meter square, okay, and we can think of a source firing, say, electromagnetic pulses, and this target has a certain area sigma. If a photon impinges on this, okay, how do you represent a photon? Not easy. If a photon, let me use a different color. If a photon impinges on this, then it's sort of captured, it's absorbed. Now we can think of a scenario for the sake of understanding cross section as we have these little, we have a gas of these atomic targets, each having cross sectional area of sigma. You have these in a volume, and we fire a light source is merely something that shoots out these H news onto it, or perhaps we can say, okay, these constitute an oscillating electromagnetic wave, and you can say that if a photon hits a target, then it gets captured. Now between two targets, between two media, one which has an alpha that is like twice the other, okay, we have two media, alpha 1 is twice alpha 2. What does this translate to? In our language, this means sigma 1 is twice sigma 2. Okay. So, sigma 1 is a medium where the atomic response of the medium, if we can use this to be sigma 1. So, all the sigma 1s are per atom twice the area of sigma 2, the blue guys. So, what does this actually mean? What matters is the number of, in terms of defining alpha, what matters is the number of these absorbers per unit volume, okay, which will capture this. So, N is a dipole density, absorber density, atomic absorber, it's the number of atomic absorbers per unit volume. Therefore, we can say that medium 1's optical density, that is optical absorbance, optical density for absorption of medium 1 is twice that of medium 2. So, optical density or OD often gets quoted as a property of a medium, optical density. Okay. If you use these components called neutral density filters, in an optics lab, you would often you would see that these are designated as OD.1, OD1, OD10 and so on. That the scale is logarithmic, so beware of that. But the point that we wish to make is that an optical density, or for that matter we used earlier the notion of 1 over alpha being optical depth. We also said that 1 over alpha is absorption depth, not optical depth, absorption depth. This is also optical, we can say this is optical thickness. We can call this an optical thickness too. That is that thickness of a target after passing through which, target medium after passing through which the intensity of the beam is diminished by a factor of E, which is a little, 1 over E is small, is about 1/3, whereas you could also have gone to base 2, but here it is naturally set in base E, right. So, these are relative measures of absorption. So, the point that we must appreciate is that sigma is an atomic quantity, it is per atom, per molecule, maybe per nanoparticle if you wish, or per unit per lattice unit or something like that. That's difficult to measure in a laboratory. What you measure in a laboratory is alpha. So, if you know the atomic density, for example, if I want to measure the absorbance of air which is surrounding us in this room at this temperature and pressure at a wavelength of 600 nanometers, it may be quite tiny, but so be it, right. Then I am not going to, it would be futile to capture one nitrogen, oxygen and whatever molecule and try to measure the individual molecules absorption, cross section and do things. Instead, I estimate how many target molecules are there, shine a beam through the medium, okay, determine the volume of the medium, determine the density of the absorbers and subsequently arrive at the absorption cross section. That is usually the way we do it, and then you can document this in for all mankind to learn about it in data tables which are typically maintained by NIST. So, the NIST website would give us this information for a wide range of atoms and molecules. Okay. So, that is the way to go about it.